So in this video, we're going to go over another use for, or a use for the impulse equation, which is that impulse is equal to the change in momentum. Um, I try to make it pretty clear that that the amount of momentum that your arrow starts with doesn't really measure anything. It's a way of specifying the state of the system. And it certainly doesn't tell you what the impulse is going to be. But one of the utilities of momentum is if you know what the initial momentum was and the final momentum was, you can use that change in momentum to measure the applied impulse. And so from that, we're able to check things like forces and at least average forces and things of that nature, if we can measure a change in impulse. So let me give you an example of this. And this is one of my favorite ones because it clearly demonstrates one of the pieces of erroneous thinking that happens in the archery community, particularly this idea that an arrow has force. I've already said multiple times that an arrow doesn't have force. Nothing has force. Force is a way of describing the interaction between two different systems. But certainly, I've seen people on Archery Talk and other places say things like, well, um, uh, if you have an 75-pound bow draw weight, then 75 pounds is the force that gets the arrow gets put onto the arrow while you're firing it, and so 74 pounds of force is the most force that arrow can now use. That somehow that 74 pounds of draw weight gets turned into 74 pounds of force that the arrow has, and that 74 pounds of force is the maximum amount of force that the arrow can produce when it penetrates something. And that's just not physics. That's just not how things work. So hopefully this will demonstrate this pretty clearly. So we're going to look at an example would be the average impact force. So what we have is an arrow, and we imagine it going through some kind of material. Probably not foam, something hard that would hit and punch through and break and then keep going. So maybe something like a MDF, or plywood or something like that, kind of a narrow piece of plywood, and it hits with an initial momentum and punches through and continues through the other side. And so what we would like to do is use this equation to measure the impulse and then use the impulse to calculate the average force felt on impacting this piece of particle board. So the first thing you do is you assign a coordinate system. So this is the standard coordinate system. We've got X running left and right. We've got Y running into and out of the screen and Z running up. I'm setting it up this way so that the entire motion, the entire momentum vector is pointed along the X-axis. And that makes it easy because that means there's only an X component of the momentum. And then we can just ignore the Y and Z components, which is going to make life a lot easier for us. So the X component of the momentum is the magnitude of the momentum. Notice this is a positive number because we defined X to be positive when moving towards the right. So because the arrow is moving in the positive X direction, its X component is positive. The arrow punches through, and now it's got some new momentum we're going to call the final momentum, which is less than the original momentum. So the final momentum punches through, and again, the component here is the magnitude of the momentum, and again, it has a positive sign because it's moving in the direction of the x-axis. So if this is our momentum, our little arrow, our vector indicating momentum initial, and this smaller, shorter arrow is our vector indicating momentum final. Notice it's shorter because we lose some momentum going through this material, whatever it is. And the difference between PF and PI is this vector J. Now notice the impulse is actually pointed in the negative X direction. And so when we write down the components of the impulse, again, it doesn't have a component in the Z direction. It doesn't have a component in the Y direction. It does have a component in the X direction, but it's actually minus the magnitude. So however big this value is, however large the impulse is, the component is minus that because it's pointed to the left as opposed to pointing to the right. But also by this equation, that vector is PF minus PI for the X component and 0 for the Y component. And so what does this tell you? It tells you that the momentum final, the magnitude of the final momentum, how much momentum it has, the actual number in slug feet per second, minus the initial magnitude is equal to minus the magnitude of the force. And then we need to calculate that. So let's go over here and look at an example. Now, this is a completely made up example. I just picked numbers that seemed kind of reasonable and that may happen. I honestly don't know what some actual numbers would be. It would be worth exploring just to see, be an interesting kind of experiment to look at. But let's say that we have an initial velocity of 285 feet per second and an arrow mass of 450 grains. That's 2 times 10 to the minus 3 slug. Slug is the standard unit of mass in the English customary system or the U.S. customary system. The kinetic energy of such a combination would be about 81 foot-pounds of force. This would be easily produced by a bow that's about 335 IBO with about 74-ish pounds of draw weight and a 28-inch arrow, or 28-inch draw length, excuse me. And various other kinds of combinations would get you this much energy, but this is kind of a standard, by today's standards, this would be a sort of a standard setup. A little bit heavy on draw weight, 330 to 340-ish bow, 28-ish inch draw length. That will get you about 80 foot-pounds of kinetic energy. And the initial momentum for this setup would be 0.57 slugs. Now let's suppose that it punches through, and we've got another chronograph sitting over on this side, and we measure how fast it's going once it comes through, and say it's still traveling 100 feet per second. So it's lost a significant amount of its velocity punching through this material, whatever the material happens to be. Mass is, of course, still the same. Now if we calculate the kinetic energy of the arrow after it's gone through is about 10 foot-pound force. And then excuse me, I put PI here. This really should be PF. So let's see if I can erase that. The final momentum, what is the final momentum going to be here is 0.2. So that's the momentum for 100 feet per second and 2.0 times 10 to the minus 3 slugs of mass. Okay, so now what we need to do to be able to work this problem is we need to be able to calculate the magnitude of J. So notice PF minus PI, PF is 0.2, PI was 0.57, so 0.2 minus 0.57 is minus 0.37. That's the minus J. So J is 0.37 slug feet per second. That's the magnitude. J is the magnitude of the impulse. The magnitude of the impulse is 0.37 slug feet per second. Okay, and then our definition of impulse is that it's equal to the average force, not the instantaneous force, but the force during the entire process of the arrow punching through, the average force times the time that it took for the arrow to go through. So let's get an estimate of that time. So how do we estimate that? Well, assume the board here was 1/2 an inch thick, and let's just to be on the cautious side. Let's assume that the arrow traveling through was only going 100 feet per second through the entire board. So that's the equivalent of saying that as soon as it hits, it dropped down to 100 feet per second, and then that's how fast it was going as it crossed this little length here, and that's as long as it would take. Now, honestly, it would probably take much less time than this because it's not going to be going 100 feet per second through the whole thing. It impacts at 285, it exits at 100. And so the average velocity that goes through here is probably more like 190, 195 if we imagine it's a linear change here. But whatever it happens to be, we're going to use 100 just because that gives the maximum amount of time that the arrow could be punching through here. So 0.5 inch, convert that to feet, and then 100 feet per second. That's 4.2 times 10 to the minus 4 seconds, or about 420 microseconds is about how long it takes the arrow to actually punch through this board. So we rearrange this equation. If we take the magnitude of the impulse and divide it by the time, 0.37 slugs divided by 4.2 times 10 to the minus 4 seconds, that's 890 pound force, and that's the average force. That's not the force as soon as the arrow hits. That's the average force that the arrow feels as it goes through this piece of board. 890 pounds of force, as opposed to the 74-pound force that was applied to the arrow at the bow. So you see these two numbers are just completely different than each other. Irrelevant. There's no relationship between this number and this number. And there's certainly no relationship between the 890 pounds of force and the .57 slugs that the arrow had of momentum. This is just it's a completely different quantity. It's a different physical quantity. I also checked what would happen if the actual average time was half of this. In other words, if you were about halfway between 285 and 100 as the average velocity of the arrow through the board. Using the average velocity of the arrow through the board, we end up with about 1,700 pounds of force being exerted on the arrow during this impulse. And again, that's the average. So this is why arrows can break bone, and why they can punch through pieces of thin pieces of plywood and that kind of thing. You would never be able to do that with only 74 pounds of force. That's just not a big enough force to break a lot of this kind of stuff. And you're just not going to get it without recognizing that the force is the interaction force, or the strength of interaction between the arrow and the board. It's not something that the arrow actually has with it. It doesn't have 890 pounds of force. It doesn't have any force. It's just the force is what is actually happening. What is the strength of interaction as this thing punches through? So that's one thing that's interesting. Let's look at another possible interesting thing, and that's this idea of punching through heavy bone. So I think some people are going to be a little startled by the following result, and it may cause some controversy, but it's fun, and so we'll look at it and see what I'm getting at. So let's suppose that our arrow is punching through some kind of bone. Here's my little dog bone for just as illustration purposes, but this would be something like a scapula or a knuckle or something like that. And so we imagine again that we have some initial momentum and then some final momentum, and that the arrow's pierced and gone through this. It's penetrated the bone. And of course, the initial momentum, the final momentum is going to be less than what the initial momentum is. So again, we can write down this equation, which should be a vector equation. So I need to have some vector arrows here. And it's the exact same equation that we saw before. And in fact, what I'm going to do is really, I don't want those vector arrows. We're going to look at this as the magnitudes as opposed to the actual vectors. So in other words, this is exactly the same setup as I had here. And so it's exactly the same equation. PF minus PI is equal to minus J. Exact same equation. PF minus PI is minus J. Same setup. But now we're talking about going through a bone instead of through a piece of MDF. Okay. Now, note that the momentum is, of course, the mass times the velocity. So the final momentum is the mass times the final velocity, or the velocity after exiting the bone. And the initial momentum is the mass times the velocity before or on impact, if you will. And so what I'm going to do is I'm going to move this this minus MVI to the other side. So I get MVI minus J is equal to MVF. So what is the condition that this happens, that the arrow actually gets through the bone and keeps going? The condition is that this value has to be greater than 0. In other words, if the velocity is 0, then that means it stopped. Or if the velocity is negative, that means it hit the bone and bounced backwards, okay, and bounced out. So in order for penetration to have actually happened, we have to have that this PF term, mass times final velocity, has to be greater than 0. All right, and so what does that mean? The condition to break through bone and penetrate the vitals is then that the initial momentum, or MVI, must be greater than the impulse. You probably could have guessed this. You could guess this from just looking at this equation. If we know the impulse is the change in the momentum, in order for us to actually penetrate bone, then the impulse has to be less than the initial momentum. Otherwise, if the impulse is greater than the initial momentum, then that means that the arrow is actually going the other way. The arrow's been bounced out as opposed to punching through. So let's look at this condition for breaching heavy bone, and let's see what we can learn from it. So we're going to make the simplest assumption that we can make. I will try to justify this assumption a little bit momentarily, but the simplest assumption that we can make, we're going to assume first of all that this impulse that is a function of the impact velocity. That is, if the arrow is going faster, the impulse that will be applied is larger. If the arrow is going slower, then the impulse that's applied is smaller. That's pretty obvious. We would guess that the average forces acting on the arrow as it hits the bone are going to go up. They're going to increase as the arrow is moving faster. That shouldn't be a concern to anyone. What may be a concern is the next part. The next part is that we're going to assume that the impulse is linearly proportional to the impact velocity. So what does that mean? Here's the graph. If we know the impact velocity is 0, in other words, the arrow's not moving when it hits the bone, well, then what does it even mean to hit the bone? It's not moving. Obviously, it's not going to penetrate. So there's no impulse if it doesn't hit the bone. So that means the impulse is 0 when the impact velocity is 0. And then what this statement says, it says that there's a linear relationship, that as your impact velocity goes up, then the impulse goes up. So that may or may not be a good statement, but basically there's a linear relationship between the impulse and the impact velocity. And there's a slope here. We typically give the symbol m for slope in mathematics, but we're already using m for mass for the arrow, so I don't want to use this slope. So I'm going to cancel that out. We're going to call it something different. But what we would say is that the impulse is equal to the slope times the x value here, which in this case is the impact velocity. And again, let's change the name. I don't want to call it slope. Let's call it something different. What do we want to call it? Let's call it HBT. We'll just call it this. You call it anything you want to, but I'm going to call it HBT, and then we'll see what HBT actually is in a few moments. Okay, so what this says is that the impact impulse is equal to some constant, which we're calling HBT, times the impact velocity. Okay, and as the impact velocity goes up, the impulse goes up with this proportionality constant, the HBT. Okay, so the next thing to recognize is that for an arrow, the initial velocity is a function of its kinetic energy. So in other words, your bow produces a certain amount of kinetic energy, and that tells you how fast you're going. And in fact, the equation for the impact velocity is going to be the square root of twice the kinetic energy initial or impact divided by the mass. So this just comes from rearranging the expression that kinetic energy is equal to 1/2 the mass times the velocity squared. And we just moved the mass down here and the 2 up there and then took the square root. So that's all this is. And so what we can then do is just rewrite this equation. We can rewrite this equation as whatever this heavy bone threshold is, and that's what we're calling this, HBT, the heavy bone threshold, times the square root of 2ke initial divided by mass. All right, and then let's look at what this equation says, or this inequality says. So it says the mass of the arrow, okay, that's what this m is, that's the mass of the arrow, times its impact velocity, but its impact velocity is just twice its impact kinetic energy divided by the mass of the arrow, must be greater than HBT times the same thing, twice the kinetic energy of impact divided by the mass. And what do we get? This term cancels this term, and the condition that the arrow penetrates the bone and goes through is that the mass of the arrow must be greater than some heavy bone threshold. So that means that when your arrow is above a certain weight, it will go through the bone, and when it's not above that weight, it won't. And that's going to freak a bunch of people out, because people have been saying for years that this idea of a heavy bone threshold, it doesn't exist and doesn't have any backing in physics. And here you go. This is exactly why physics could explain, and very easily could explain, what's called a heavy bone threshold. So anytime you get a result like this, maybe something that doesn't make intuitive sense, because it should be pretty clear that I think I've heard Bill at Iron Will say this. You take that 700, 800 grain arrow and you throw it at a Cape Buffalo, it's not penetrating the bone. So velocity has to play a role. So when you see something that looks like this that says the condition that you're going to penetrate through the bone is that the mass is above a certain value, you definitely have to go back and double check your assumptions. So the assumptions that we made here, the only real assumption that we made was that the impulse, the impact impulse, was linearly proportional to velocity. Now, this is clearly not going to be true, but it will be true over small, short changes in velocity. Meaning, it doesn't matter what kind of function you have. I'll put up a new sheet here just to look at potential functions. You imagine we have some kind of function like this that may have any kind of weird shape associated with it, and this might be impact velocity versus impulse force or something like that. And what you can always do is you can always look at small segments of it, and over some range of velocity here, that will a line will approximate that segment. That line won't approximate the rest of it. It doesn't look like the rest of the function, but it does look like that one part of the function. Same thing here. We could look maybe over from this point to this point, and we could imagine that there's a line that's pretty close to looking like that over that range. So as long as you're in this range, it looks linear. And as long as you're in this range, it also looks linear, but the slope for this part of the graph is very different than the slope for this part of the graph. So let me pull up an example of this so that you can sort of see what this looks like. So here's a graph of a function, and you can see this is actually the square root of x is the function here. You can notice that say over this region here, say from about 0.2 to 0.4, that's pretty straight. And a straight line there would have a slope that you could approximate, and that slope would correspond to a heavy bone threshold. But as you would go up in impact velocity, that slope will actually get a little less. This part also looks linear, but it's linear with a slightly less slope. So here is a sort of a demonstration of that. Let's say that we could look at this portion of the graph right here, and you would say that from this point to this point, the data and the line are very, very closely approximated to each other. And so in this range of velocities, you might see a heavy bone threshold that matches this slope. But as you go to higher and higher velocities, you might see that the line is better approximated like this, where perhaps we have this range from here to here, that's the line, and that has a different slope. And you would say that in that range of velocities, the heavy bone threshold, well, let's see, the slope is less steep here, so the heavy bone threshold, the mass of the arrow required to penetrate, would actually be less for this region of the graph than it would be for this region of the graph. Now, I am not saying that this function is the correct function. I don't know what the correct function is. I don't even know if there's a function that you can write down analytically. You could certainly graph it, but it might not be something that's like, the natural logarithm of the velocity or the velocity square root of the velocity or something like that. It could be, or it could just be something that you can't express analytically. Nevertheless, it will still be true that over small changes of velocity, say that you're studying things moving between, 150 feet per second and 180 feet per second, you might find that there is a particular threshold value for the mass of an arrow above which you get significantly increased penetration in bone. And what do I mean by that? So let's go back and again look at some of these pictures. So let's imagine this is a normal distribution, and what I have on the vertical axis here is the number of occurrences, and on the horizontal axis here I have the quote heavy bone threshold. And now what this is saying is, and I should make this clear about this model as well, this is not saying that this is true for any animal. This is saying this is true for a specific circumstance. This number would actually change depending on with the same animal, depending on where you hit it. So this is not something like that you could say such and such is the heavy bone threshold for every single instance that you might encounter. No, you would have a distribution. So sometimes, for some animals, penetrating the bone is going to be much lower in mass, and for some it would be much higher in mass. And so what you get is this kind of distribution, this distribution picture, where if your arrow is say the heavy bone threshold is 300 grains, for the case of I don't know whitetail rib bones. Okay, so whitetail rib bones below 300 grains. Below 300 grains, you have a strong likelihood of not being able to penetrate the rib. And anywhere above 300 grains, you have a really good chance of penetrating the rib. That would be the case here. And so the point is, what you do is you do that for a bunch of different animals. And you'll find that the HBT, depending on where you hit the animal, whether it's scapula or femur or rib bone or whatever, you could say, okay, you could do a bunch of studies and find what is the HBT for that animal in that spot. And then you could do another study on a different animal and look at all the different spots there and so forth and so on. What you'll find is you'll get a distribution. And I don't know where that distribution is centered. This is just, again, speculation. But suppose that you get a distribution that looks something like this. And what that would tell you was that in most cases, if you have a 400 to 500 grain arrow, if this were the distribution, you would have a good possibility of quote busting through any bone that you might encounter. And this would be the HBT at the low velocity end of our picture. So that would be sort of this kind of slope. But on the other hand, if you have a higher mass arrow, 600, 650, 700 grains, then you start to beat the curve where all of the possible different locations are below you. So you're almost guaranteed to be able to break the bones within reason, within whatever percentage of occurrences that you actually studied here. So let's say you checked going through some extremely heavy bone and you just didn't find any mass that worked. Well, then that would not be on this chart because that would be somewhere way out here, and so it just doesn't show up. So this doesn't guarantee that your arrow is going to work if you're above a certain mass. What it does guarantee is that in most cases it will perform better than in other cases. And what happens if you change your velocity range? Instead of, say, the trad bow velocity range, you change it to something that looks more like a this, where the slope is less and a higher velocity range, like you might find with a compound bow. Then what happens is that this whole curve just gets shifted this way. And so instead of being above 650, maybe it's above 575, or maybe it's above 525. And basically being in different sections of this graph results in a different peak location for this distribution curve. And so I think that's the interesting take home here. First of all, is there a physical reason why a heavy bone threshold could be seen in experimental data? And the answer is absolutely yes. You could see this, particularly if you are studying over a limited range of velocities. So if you're only looking at 140 to 180 feet per second impacts, that's a relatively limited range of velocity, and over that range of velocity, the relationship between the impulse and the impact of velocity could be linear enough in that region that you would get a threshold mass that most arrows, if an arrow is above that mass, you're going to get an increased number of successful penetrations, whereas if the arrow is below that mass, you're going to start seeing issues of the arrow not going through those bones. But then you go to a faster arrow by going to a compound bow, and you're shooting down the 265 to 295 range. And now you might find that if you do the exact same experiments again, you may find that this number, this slope, is more along the lines of 500 grains or 520 grains. Again, I'm just throwing numbers out there because we don't have enough data. The Ashby Foundation has produced data, at least in the Ashby reports, mostly for lower velocity things. I know that there is data that they say they have data for compounds and they collected data for compounds in crossbows and higher velocity arrows and bolts, but I haven't seen that data. So I really don't know what the numbers are, but what this is a theoretical justification for why a heavy bone threshold may be observed over a range of velocities when studied over a range of velocities with a particular kind of bow. So that's another interesting application of the impulse equation.